I would like to recall the definition of the derivative of the function f, that denoted by f prime x, is the limit of fx plus h minus fx over h when h approaches 0, if this limit exists and finite. Since the limit in the definition of the derivative is related to h, the limit, which is the derivative of f, is another function of x. Because the derivative is a function of x, we are most likely able to differentiate it again, if it's possible, which means if it is differentiable function. Think about differentiation as a machine. The input and the output are functions. Here's the machine that differentiates. It means that if you put a function in, then you will get the derivative of the function out. But because this is a function, we can now put this again in the machine. And we will get the second derivative, because it's the second time we are differentiating the function. But this is a function as well. So why not to take this function again, differentiate that, and to get a new function? And again. And again and again. So if the function can be differentiated again and again, and most functions that we know, like polynomial and rational functions and exponentials and logarithmic functions, or all the functions that we are aware of, really can be differentiated again and again, as many times as we like. The notation for higher derivatives can be really confusing, so let's go over that. Let's assume that y equals f of x. The first derivative can be written as y prime or f prime because y equals f. Using the Leibniz notation, we can write dy dx or d dx of f. Second derivative. It is y double prime, f double prime. And using the Leibniz notation, it's d to the power of 2y over dx to the power of 2. Or d to the power of 2 over dx to the power of 2 of f. But we just say second derivative of f. The third derivative is going to have 3 primes instead of 2. And here we are going to have 3 instead of 2. So you can figure out what's going on. For example, for the nth derivative, here we have n primes. But if n is very large, we don't want to have many primes. It's really hard to count. So we write y to the power kind of n in parentheses. But this is not the power of. When you see y n in parentheses like this, it means that this is y and you have n primes. Then you have that. And here actually the less confusing notation is the Leibniz notation. Instead of the 2 or 3 or whatever, we just write n. And here we write again n. Let's do an example. The first derivative of the function f(x) is cosine x plus 10x to the power 4. The second derivative is the first derivative of the first derivative, so it is negative sine x plus 40 times x cubed. The third derivative is negative cosine x plus 120x to the power of 2. I don't know what is the n derivative because I don't know what is n. As you can see, most likely we will have to go through the steps. So if I will ask you what is the third derivative of the function, you really have to go to the first derivative, to the second, and to the third. Example. What is the second derivative of ln of 3x plus 5? We have to start with the first one. And the first derivative is 3 over 3x plus 5. And we have to differentiate that because, again, the second derivative is the derivative of the first derivative. Now we just use the quotient rule and we get that. Simplifying and you get this. Another example. The second derivative of x to the power of 2 times e to the x. Product rule can be really nasty when you have higher derivatives, but I will show you a way to make it a little bit better. So this is the first derivative of the first derivative. For the first derivative, we are using the product rule. Now you have two choices. If you want now to differentiate this function, then you can see it's a product plus a product, so you will have to use twice product rule. I can save time and do only one product rule by first writing the first derivative as e to the x times 2x plus x to the power of 2. Now I have to apply the product rule only one time. And when I apply, I get this. Again, we can simplify this a little bit by distributing e to the x, and now simplify that. And we get this is e to the x times 2 plus 4x plus x to the power of 2. Find the second derivative of 1 over x plus 3. Again, it is the derivative of the first derivative, and the first derivative is negative 1 over x plus 3 to the power of 2. We have to use the quotient rule, and we get this. We can a little bit simplify here. We can cancel x plus 3. And also, if you look, then we get negative 1 times 2, which is 2. We can also do it in a different way, using the chain rule. I'm going to write 1 over x plus 3 as x plus 3 to the power of negative 1. I'm going to use now the power rule for derivatives plus a chain rule, but the chain rule is very easy because if u is u equals x plus 3, it's the inner function, then dx equals du. It's kind of, if you want, the trivial u substitution, and I get that. Now it's easy to apply again the power rule with, again, the trivial chain rule, because the inner function x plus 3 has a derivative of 1. And I get that this is 2 times x plus 3 to the power of negative 3, which is exactly as I got before, obviously, because derivatives are unique. Find the 98th derivative of the function fx equals sine x. Oh, don't scream! No need to scream in this case. Usually, to find the 98th derivative of a function, we will need to go through the process of doing the first derivative and the second and the third and the fourth and the fifth and the sixth and so forth. But not in this case. You will see why in a second. We will start with our function. The first derivative is cosine x. The second one is negative sine x. The third one is negative cosine x. And the fourth one is our original function. What does it mean? It means that every 4 steps, I'm back to sine x. I call it kind of a loopy function, because it is loopy in a way. The fifth derivative is this is the 6th, this is the 7th, and what is the 8th? Again sine x. And what is the 12th derivative? Sine x. And the 16th. And the 20th. And also the 96th, because 96 is divisible by 4. And each 4 steps, we are back to the original. It means that the 97th is cosine x, and the 98th derivative is negative sine x. Now I would like you to find the 98th derivative of the function fx equals e to the x. We take e to the x, and we take the first derivative, and we are back to e to the x. What happens about the other derivatives? All of them are just e to the x, and we can actually conclude that any derivative of e to the x is e to the x.